Okay. Hello everyone, this is Engineer Salasi from Halo Academy and Brave Boosters. In the last video we covered the chapter 1 and chapter 2 of this book. So operating systems in 3 pieces. And today we are going to start chapter 3, virtualization. So by now I am expecting that you have some good knowledge about operating system, what is virtualization, how CPU is virtualized, concurrency, and persistency. These are the 3 concepts we discussed last time. So without further ado, let's go and discuss chapter 3 and chapter 4. So chapter 3 is just a dialogue with a professor with the student, but I recommend you to go ahead and read it because it will give you good idea about what is virtualization, and the professor demonstrate this with a good example, so it will give you some idea, and I really recommend you. So the idea of virtualization was discussed in a pretty simple example of pitch and ether relationship. There are a lot of ethers but only one pitch. It was a great example, at least for beginners, to start thinking about CPU virtualization. So I recommend you go and read chapter 3, just 1 or 2 pages. Then chapter 4, the abstraction, the process, operating system, 3 pieces. So let's get into it. What is process? So CPU virtualization, the operating system can promote the illusion that many virtual CPUs exist, but in reality we have only one CPU. But this time, because there are other, maybe you could have 2 or 3 CPUs, but in most cases we have only one CPU. But the operating system creates this illusion that every process, when it runs, it assumes that it has its own CPU. This CPU virtualization is achieved by time sharing. Time sharing, running one process and stopping it and running another. This is the way how virtualization is achieved. So there we have time quantum. So the process will run for some time, then when the time quantum reach, the CPU will, with the scheduler, preemption. We have preemption type of process system. So it will be preempted and another process will continue. And this kind of time sharing with a short-term scheduler and operating system and hardware do this magic. So time sharing is a big concept. So in general, a process is a running program, because a program by itself is lifeless. Okay, as you can see, program itself is lifeless. It just sits there on the disk. Okay, when you have a program, it will be in your secondary disk and it doesn't do nothing. Okay, it has a bunch of instructions and maybe some static data waiting to spring into action. So a process means a running program, but a program by itself is it sits in the secondary memory and it doesn't have any action. But to be executed, all the program, the needed programs should be loaded into memory. Okay, the primary memory. Then the CPU will take whatever it needs. It is operating system that takes these bytes and gets them running, transforming the program into something useful. How to provide the illusion of many CPUs, although there are only few physical CPU available. How can the operating system provide the illusion of a nearly endless supply of said CPUs? These are very good questions, That's what the technology is, what is the operating system does. The operating system creates this illusion by virtualizing the CPU. Virtualization means it creates virtual CPUs and memory. By running one process, then stopping it and running another, and so on, the operating system can promote the illusion that many virtual CPUs exist when in fact there is only one physical CPU or a few. So when the process, if you open your task manager, you can see a lot of processes are running. A lot of how this happens, because you have only one CPU, so one process at a time should run. But as you can see, a lot of processing programs are running there. Why? Because of virtualization. That means by time sharing. We have time quantum, so the process will run very, significantly small amount of microseconds, and it will be removed, preempted from the CPU, and another will come and it will go. That this movement, rotation seems like all the processes are running at the same time, but that's not the case. The basic technology known as time sharing of the CPU. So time sharing of the CPU is, what is it? This is a technique used in operating system. Time sharing of CPU refers to the ability of user to run multiple processes simultaneously on a computer system. This technique allows for greater efficiency and productivity, as users can work on different tasks at the same time. And working, when a user initiates a process, the CPU allocates a certain amount of time to that process. Once the time limit is reached, the CPU switches to another process. This process continues until all process has been completed. The advantage of this time sharing is, the main advantage of time sharing of CPU is that it allows for the concurrent process of multiple tasks, which increase efficiency and productivity. It also enables users to share computing resource, reducing costs and improving overall system of performance. The disadvantage will be, however, the downside to time sharing is that it can result in decreased performance, as the CPU must be shared among multiple processes. Each process runs more slowly as a result, and the overall system performance can suffer. In conclusion, time sharing of CPU is a basic but essential technique used in operating system. It enables users to run multiple processes simultaneously, increasing efficiency and productivity. However, it can also result in decreased performance if CPU is heavily shared. So this I hope it will help you very much. Virtualization, time sharing, how the CPU is virtualized, and memory. We have seen these concepts in the second chapter, first and second chapter, and you can refer that video as well. Then to implement virtualization of CPU and to implement it well, the operating system will need both some low-level machinery as well as some high-level intelligence. This is mechanisms, the mechanisms and the policies. These are the basic points. We call the low-level machinery mechanisms are low-level methods or protocols that implement a needed piece of functionality. For example, we will learn below how to implement a context switch, which gives the operating system the ability to stop running one program and start running another on a given CPU. They always answer the how one program stops and the other program will continue. The running program will preempt it and continue. This kind of how questions will be answered by the mechanisms. On top of those mechanisms, resides some of the intelligence in the operating system in the form of policies. So policies are algorithms for making some kind of decisions with the operating system. In general, policies answer the which question, which program should come now, which program should run now. okay, in the CPU. So for example, given a number of possible programs to run on a CPU, which program should the operating system run? A scheduling policy in the operating system will make this decision, most likely by historical information, workload knowledge, performance metrics, which program has run more over the last minute, what type of program are running, is the system optimizing for interactive performance or throughput. So the most important thing we should know is that virtualization of a CPU is achieved by mechanisms and policies. So what part of the machine are important to the execution of a program? So when a program runs, what is comprising of a process? So when a process runs, we have memory address space, we have registers like EX, EBX, and we have also input-output, okay, conditions. So when we say memory, both instruction and data section are in the memory, because as I told you, as we have discussed now, a program is just lifeless until it starts executing. So a process means a program in action. So to be in action, to transfer from a program to a process, all the codes, instructions, data should be loaded into RAM in the memory, first memory, because the program is in the secondary memory. So in that way, the memory is part of the process. Then we have registers, we have program counters, RIP, tells us which instruction of the program currently being executed, stack pointers, RSP, and frame pointers, RBP, used to manage the stack for function parameters, local variables, and return addresses. Finally, programs often access persistent storage devices too, such as input-output information, might include a list of the files the process currently has opened. So these are some of the points that comprising a process. We have also APIs, application program interface. You know what does it mean, APIs? We have discussed this in chapter 2, because operating system is an interface between the user and the hardware, and the users to interact with, to use the whatever the available services from the operating system, they use APIs. So these APIs are available in any modern operating systems like create, destroy, wait, miscellaneous control, status. All these are the APIs. Create a new process to run a program, fork, exec, clone, destroy. These are also alt a running program, kill, because you can send a signal to the running program by using kill, and you can stop it, and you can also resume it. Wait for a process to stop running, because in the case of fork, because fork and the exec are two types of very important APIs. The fork will create another child process which is the same as the parent process, but the PID will be different. So if we don't use wait in the fork new program creation, the parent program will terminate first, and the child program which is created will become a zombie state, because the parent program is closed before the child is terminated. So when we use wait, the parent program will wait until the child process terminate, then after that the parent will terminate. So we will see it. I will show you good example when we just in a minute, okay? So we have miscellaneous control, some kind of methods to suspend a process and then resume it, kill it, like this. And the status, get some status info about a process, we can use cat command, process PID status, then it will give us the process. So these are some of the APIs, but we have a lot of APIs, and you can go to the main page of Linux and you can read there. So as you can see, let me program Linux demonstration. You can directly, this is just to show you what is a program and what is a process. If you go to you can download this. Okay, it's free from the website. Okay, from the website Andrea. So let me show you. Okay, let's open. Let's open this and let's okay, let's go out from here. I want to open the introduction part. This is our first, so let's open the terminal, and if you see, these are the files we have, the programs we have in the introduction part. So what I want to show you from here is what is a program. For a program is just sit in the it sits in the secondary hard disk, so it's lifeless. So just to see the programs, what we do, for example, if you want to see alpha files, these are, as you see, these are alpha programs. Okay, and if you want to see like the content of the program, as you can see, these are programs: CPU, ELF, IO, memory, thread. We discussed this then. If you want to see what is in the program, you see, these are just a program. Okay, this is just a program, just for the demonstration purpose. Okay, you can download the files, the programs. Remzi and Andrea, this open source. So let's continue. Okay, now let's memory. Now what I'm going to show you, as we have seen, the program constitutes memory, register, input output information, or Linux demonstration. So what we are going to do is the same. Let's clear this. Okay, let's clear this. So what we are going to do, let's just use my using cpu.c. Okay, no, cpu.s. Okay, so what we are going to do now, cpu.s. Then let me pass now something. I want to execute this CPU. Let me write my name. For example, let me say Selassie. This is my name. Now let me run. Now as you can see, this program is running. Okay, this program is running. Now let's open another terminal. Okay. Now, as you can see, this program is running already. Okay, this program is running already. Now let's get information about this running program. Okay, let's get information about this running program. So what we are going to do, the first step, we open this and we pass in an argument, and we initiate it, and the program is running now. Now let's get information. Let's use ps aux, because we will open another terminal, execute some commands. Okay, so aux grep, okay, grep cpu dot else, cpu dot else. So as you can see now, this is the information getting. Okay, this is the information we are getting. Again, let's do ps grep let me make it less. Okay, this one which I cannot see. Okay, I hope you can see now. Color is equal to auto CPU dot else. Sorry. Sorry, I make mistake. So what we are going to do, once we get the information, that one is okay. So what we are going to do, okay, grep CPU dot else. Okay, as you can see now, we get the PID. Okay, we get the PID. So we can come here and the explanation. Once we get the PID, using the PID, we will use this PID to get any information about the process, because once you have the PID, we can get any information we want about the running process. Don't forget the process is running. Okay, the process is running. This, as you can see, it is running. Now what we are going to do, general information can be found about this particular process, okay, by using the process once we get. So what we are going to do now, let's get information now. Cut, okay, cut process now 252585, okay, and status. So as you can see, once we use this formula, you see CPU.elf, and we have running. Now the process is running, the status is running, and if you go down, the PID is this one, And if you go down, you see the memory. The memory information is also given here. The virtual memory, you see, VMHWM, VMRSS. So this give us an idea that we can get information about the process. Okay. So the next step, what we are going to do, let's see the file descriptors. Okay. For input output, we have standard pre-opened file descriptors. So for example, 0 is a standard input, 1 is a standard output, 2 is a standard error. Just to see that, what we are going to do, ls, just write this command, and the PID we have to bring from here. This is the PID. Copy. Paste it here. So the PID will be here, and what we are going to do, the file descriptor. So as you can see, 0, 1, 2. This 0, 1, 2 means 0 is for standard input, 1 is for standard output, and 2 is standard error. Okay. So once we find this, let's show you what standard output means. That means if I send the signal to the running program, this one, this is a running program, let's sit here, and this is our second program, yeah. So sorry, what I want to do, I want to show you now. Sorry, let me make it like this. So the program is running, the upper one is running. So I'm going to send the signal for standard output. Okay. So what I'm going to do, I'm going to use this. Okay, I'm going to use this. So you can see now. Okay, let's send the signal now. Echo standard output standard out. Standard output. Then what we are going to do, process the PID. This is our PID, file descriptor 1. So if I run this, yeah, you see, so the standard output is already up here. So we send the signal, and we have seen that. That is what I wanted to show you. So don't forget, we are writing to the standard output here, and we have 3, like the standard input, standard output, and standard error. This is a file, pre-opened file descriptors. So the other demonstration, what I want to show you is that the standard output we have seen. Now the command IR allows us to see information about the register. So what we have seen is, when we start here, what we say, the memory, the register, and input output. So the input output I have shown you now. We have seen now the memory. We have seen in the first demonstration. Now let's see the register. Okay, the register. So how to get information about the register? So the command IR allows us to see the information about the registers, and what we are going to do now, let's come here and let's use this formula. Okay, now debugger, let's open the debugger, sudo this one. Let's give the password. So as you can see, okay, so what I wanted to show you, okay, let's continue. C to continue, so click C, enter. Okay, so once we are in the debugger now, let's see the IR. Let's give IR command, okay, to see the register. You see, this is the register. Okay, so RAX, RBX, RCX, RDX, RSI, RDI, RBP, these are the register, okay, the register information. Okay, and once we get the register information, if you want to see, for example, the register information about, for example, RIP, what is RIP? Program counter. So let's continue, and what we can do, IR, and use this and RIP. So you see, this is the information about RIP. Again, if you want to see the stack pointer, RSP, and the frame pointer, the same thing. What we are going to do, IR and RSP. Okay, this is RSP. This is the information, IR and RBP. This is the information. Sorry, RBP. IR. Sorry, IR. RBP. So this is the information. So in this way, you can find the program counter, the stack pointers, RSP, RIP, RBP used. So what program counter is, tell us which instruction of the program currently being executed. Stack pointer and frame pointers used to manage the stack for function parameter, local variable, and internal disk. But in this short demonstration, I've showed you the process memory, because a program when it runs, the process constitute the memory, the register, and input output information. So in this way you can see easily. We can demonstrate using the Linux. Okay, hope that helps you a little bit. Okay, so process creation. What is process creation? A little more about how the process created. Okay, one mystery that we should unmask a bit is how programs are transferred into process. Program is just sit in the secondary memory, and not executing. So the process means a program in action. Okay, especially how does operating system get a program up and running? How does process creation actually work? The first thing that the operating system must do to run a program is to load its code and any static data, initialized variables, into the memory. Because as per Newman's architecture, this is the requirement. You have to load all the required codes, instructions, everything into the primary memory and into the address space of the process. Okay. Programs initially reside on the disk, okay, or in some modern system, flash-based SSD, in some kind of executable format. That the process of loading a program and the static data into a memory requires the operating system to read those bytes from disk and place them into the memory somewhere. In early or simple operating systems, the loading process is done eagerly because they put all the loads once. But this time we cannot do that because the RAM is very limited, the memory. You cannot put all the instruction and codes of all the program at once. No. Lazily means in this time we are loading our program lazily, all at once before running the program. Modern operating systems perform the process lazily by loading piece of code or data only as they are needed during program execution. Remember this term, paging and swapping. So we have paging and swapping. So whenever the part of a program needed, then it will be loaded in the RAM and it will be executed. Once the code and the static data are loaded into the memory, there are a few other things the operating system needs to do before running the process. Some memory must be allocated for the program's runtime stack. So just in the stack, because we have two types, dynamic and static allocation. So when we are using stack, so this stack, the memory should be allocated. But if we need in the process any additional memory, then we use malloc, memory allocation dynamic API, then we can use that. So load a program code into a memory, into the address space of a process. Program initially reside on the disk in executable format, ELF or P. I am using ELF now, if you realize. Operating system perform the loading process lazily, load piece of code or data only as they are needed during program execution, because our RAM is only maximum of 8 GB or 16 GB, so you cannot load all the program at once. So lazily, but in the former recent times, they used to load like batching operating system and something. They used to put all the program at once. The program runtime stack is allocated. So in C programming, use the stack. Stack is used for variables, function parameters, and return addresses. The operating system will also initialize the stack with the argument argc. This means argument count, and the argv, argument vector array of many and main functions. Okay, these are the functions argc, argv, and main functions. In addition to the stack, we have heap. So if you see the memory architecture, we have heap in the above location, and down we have stack, and in the middle it will be as needed. They can go in both ways. The program heap is created. The operating system may allow create some initial memory for the program heap. In C programming, the heap is used for explicitly requested dynamically allocated data. The heap is needed for data structures such as linked list, hash table, trees, and other integrated data structures. Okay, so heap we use malloc. You see, malloc means memory allocation. This is the function API we use to allocate data memory space in the heap. Used for extremely requested dynamically allocated data, program requests such as space by calling malloc, and free it by free API function. The operating system some other initialization tasks, for example input output setup. For example, in Linux system, each process by default has 3 open file descriptors. Each process by default has 3 open file descriptors: standard input, output, and error. We have seen this now, and I'll show you also. Thus, descriptors let programs easily read input from the terminal as well as print output to the screen by loading the code and static data into memory, by creating and analyzing a stack, and by doing other works as related to I/O input-output setup. The operating system has now finally set the stage for program execution. So start the program running at the entry point, namely main. After that, by jumping to the main routine, the operating system transfer control of the CPU to the newly created process, and thus the program begins its execution. This is just a brief explanation. I hope you get the point. So this is the formula. This is the code we use: ls proc, and this just put the PID number and the file descriptors, and it will show you the file descriptors. We have seen that. So this is just as we have discussed, this is the disk, the secondary disk. We have the primary memory, and we have the CPU here. So if you have a code, if you have a code here, a static data heap, this is the program. So how we are going to load it? So what we are going to do, loading takes on disk program and reads it into the address space of the memory. So it will take it, and all the code and everything, it will be taken into the memory, and we have stack and we have heap here. So this is how the process starts. This was a program, but when it comes to the memory, it will become process. So this is a simple diagram that the CPU can take any code of lines it needs from the memory, and the execution will continue. Okay guys, so what we are going to do, let's load debugger. Okay, this is one of our file. You can find it, you can download it, and we are loading now. Okay, we are loading. Then let's see the info functions. Okay, this is it will show us, it gives us the list of functions, as you can see. So what we are going to do, let's make a breakpoint. Let's make a breakpoint at main here, at main. So what we are going to do, like this, main. So let's run it. Now we are running it, and let's this pass. Okay, this was okay. So as you can see, this is we are running it now. So just press Ctrl and Shift, Enter, and once we go here, now let's to make it more visible, this assembly flavor in there. So let's resource. Okay, so as you can see, this is it's more clear now. So if you go and see 60, as you can see, open, we are going to open this call. Okay, so what we are going to do, let's go and see the process ID. Okay, let's open, download here. So this is we open another terminal. Okay, so what we are going to do, let's check the PID of this running process. We use PS A grep and io.health. Sorry, we make a mistake. Sorry. PS A, and we have to have this, and grep io.health. Okay, so 4415 is our PID number. Okay, now we will go to the debugger. So in the debugger, what we are going to do, in the debugger, let's go here. Okay, in the debugger, what we are going to do, first let's quit, and what we are going to do, we will follow this one. We see, let's make the breakpoint at 60. We saw at 60. Okay, so we have the breakpoint now, and we have count. Okay, let's discuss. Okay, so at this point we have seen that the file descriptor is so before we are running, let's go and see the file descriptor here in the second. What we are going to do, we will go here and let me show you the file descriptor. Okay, so what we are going to do, ls the PID is 4415 and file descriptor. So as you can see, we have 3. So what we are going to do, we will go to the next file, the debugger here. Okay, we will go here, we will go to the debugger, and we will as you can see, once we at this point, we go to the second terminal and here by ni command. So let's quit from here first. Okay, once we quit, then let's make. Okay, so now let's go to the second here, and now let's check. Now we are expecting 3 files because we open already the file. So 4415 file descriptor. So as you can see, we have 3 now. Okay, we have 3. So this is what I wanted to show you. And okay, let's continue now from here. So from here, what I showed you now is once we so the file descriptor, it was 2 first, but once we run this program, it's become 3. Okay, so as you can see, it is 3 now. Okay, so at this point, what we see is that the creation of the new file descriptor, open plt, this is 60, number 60, this system call open a file, so the file descriptor at this point shall be 3. That's what we have seen now. So a process can be one of three states. Let us talk about the different states a process can be in at a given point. So let me give you, I have this huge, let's briefly let me tell you, once a process, if you want, we have new, ready, run, and termination. These are the main states. But in addition to these states, we have wait and block states for IO operations, and we have suspend wait and suspend ready. So what does it mean? Let me go through very quickly. Okay, new means at this point the process is not created yet. Okay, the process not created. It is also in the secondary memory. It is just a program. Okay. Once from new to the ready state, in the ready state the process is created at this stage, it means the process is ready to run. So when it comes in the ready state, it means it is in the main memory and it's just waiting for the scheduler to go to the CPU and run. Whether if it is completed, it will be terminated. Okay, so the CPU, this run state is in the CPU already in the main memory. Okay, it is running with the CPU. The process is running means the CPU has been allocated already. So we have a scheduler here from ready state to run. We call it is schedule. The process is schedule or dispatch. So we have short-term scheduler at this point. Okay, for preemption mode, as per the time quantum, the process might be preempted. Okay. If you have a preemption mode, non-preempted and preempted mode. So if it is a preempted mode, then once the process is running, if it is the time quantum reach, it will be preempted and it will be put in the ready state. And if the program needs an IO request, if it has an IO request, then it will be in the blocked state. This is also in the main. Then once it finishes its IO operation, then it will go to the ready state, and again it will be scheduled by the mid-term scheduler, short-term scheduler, and it will be run, and if it is completed, then it will be terminated. Now we have suspend wait and suspend ready. What does it mean? As you know, our main memory is very limited. So once the programs are becoming the main memory, then it will be full. So what the operating system will do, it will take the process from wait state to suspend state in the secondary memory. Okay, and this will be done by the mid-term scheduler. Again, once it is completed, it can be go to the blocked state, and it will be in the ready state. Then from the ready state, it will be run and it will be terminated. The other is the from suspend wait from secondary memory, it will be sending to the suspend ready again. This suspend ready also the same, because when the programs came from new state to ready state, the RAM might be full. So what the operating system will do, it will take it from the ready state to suspend state, then when from the ready state, it will take it to resume. So that is a long-term scheduler here. Long-term scheduler pick processes from new state to ready state. Okay, the long-term state. It's also decided the degree of multi-programming, because how many programs should be stayed in the ready state will be controlled by long-term scheduler. So degree of multi-programming means the maximum number of processes that can be reside in the ready state at one time. Okay, at a given time, maybe 100 or 50. It depends. So the long-term scheduler will decide that one. Short-term scheduler will decide which program to pick from here to the CPU. So as you can see, it is not a process, it is a program. When it is in the new state, it is not a process, it's a program which is in the secondary memory. It will be picked by the operating system and will be put in the main memory. The process is about to be created at this stage. So process completed here, IO is completed, then still suspended, then it will be taken here in the suspend ready state, and then it will resume to the ready state and it will continue. So in short, as you can see, this is the most important thing and important discussion. We have two types of processes. We have CPU bound process and IO bound process. That is, CPU bound processor, the process most of the process which are in the ready queue are CPU bound. Okay, the performance of the system and the CPU will be depend on the decision taken by the long-term scheduler, because the long-term scheduler is the one who pick the processes. So which kind of process the long-term scheduler picking have huge impact on the performance. So case one, if the long-term scheduler choose more IO bound processes, then there will be more and more context switch, because the process will come here, it will come to here, it will be in the block state. Again, the process will come, again it will be, because IO operation, then it will come in the here. So there will be more context switch and the CPU utilization will be low, because it will be always context switch. The second case is if the long-term scheduler choose more CPU bound process, the CPU utilization will be maximum. But the process in the waiting state, input output here, in the waiting state will face starvation, because the CPU will be busy. So long-term scheduler should choose a mix of CPU and IO bound. In that case, the performance will be good, our system. So frequency use of the schedulers, as you see, mid-term scheduler, short-term scheduler, long-term scheduler. So most of the time, short-term scheduler is busy and frequently called, and mid-term scheduler is the second one, and long-term scheduler will be the last one. So in general, we have new, ready, run, termination, and wait block states, and suspend wait and suspend ready. And we have a mid-term scheduler for this part and for this part, and long-term scheduler for new state and ready state, for mid-term scheduler from wait block state to suspend wait, and for mid-term scheduler from ready to suspend. It has two places here, as you can see. So short-term scheduler from ready state to run state, it will be like that. So I hope you get the idea of the process states. So just to what we are going to do, let me demonstrate. Okay, let's go to our Ubuntu. Okay, so what we are going to do now, we are done with these things, yeah. So let's close this, close the terminal, and let me open new. And what we are going to do here, let me open CPU.elf, and like this. Okay, now the process is running. So let me open another terminal, the same. So we have two terminals. One is running, as you can see. So the other one is here. So what we are going to do, I want to check top. So as you can see, you can check a lot of things about this program. Okay, the status of the program, it's like equivalent to the task manager. Okay, equivalent to the task manager. So what I want to do, just I want to show you. Let's check grid. CPU.elf. So 17248. So let's check the status. So cut. can use you can follow me, okay? And 17248 and status. So as you can see, the program is running. This is the CPU utilization. This is the every import. This is the memory usage. The memory usage, and you can get more information. As you can see. So the other thing what I want to show you is if you need more of the MAM page, what I want to show you, you can use this formula MAM PS. What if you go to MAM PS, if you see PS, okay, reports a snapshot of the current process, okay, the progress. So you can process state codes. If you need process state codes, you go like this. As you can see, process state code. As you see how many process we have: uninterrupted sleep, idle kernel, and thread, running or runnable, interruptible sleep. You see, this is zombie and the like. Okay, so that is one thing I want to show you at this stage. And if you want to send the signal to the running process, what we can do, let's quit. Okay, what we can do, the process ID, we have PID 17 this, yeah. So what I'm going to do, I am going to send, now this program is running, okay, this program is running. As you can see, it is running. So I'm going to send a signal, okay, I'm going to send a signal to stop it, okay, to stop this. So what we are going to do, as you can see, let me make it like this. So I will use kill, stop, okay, then the PID, paste. So automatically, as you can see, it is stopped here. Okay, so this is another API which we can use to stop. If you want to continue, what we can do, kill count and the PID count. So as you can see, sorry, this one is should be like this. It is take care, it is case sensitive, okay, case sensitive. So as you can see, now it's running. So in this way you can stop or you can continue the running process, okay. And the last one, maybe I can show you, so to check the status, when it is stopped, it is stopped. When it is running, let's check now. Okay, let's check that the process status. So then let me put here and others. So as you can see, you can come here. Now it is running because we continue. Okay, the operating system has some key data structures, and these data structures that track various relevant pieces of information. So process list, ready process, blocked process, current running process. So the operating system has data structures. Register context will hold the values of the register copied to a data structure in the memory. When a process is stopped or paused, everything will be recorded, will be copied back to the actual registers during a context switch to resume the stopped and pause the process. And we have also process control blocks. The C structure that contains information about each process. A fancy way of talking about structure, C structure that contains information each process. So this is also very important. So this is XV6. This is an operating system, saves and restore the register. This is register to stop and subsequently restart a process. So structure context, what we have: EIP, ASP, EBX, ECX, EDX, ASI, EDI, EBP. This is index pointer register, start pointer register, called the base register, called the counter register, called the data register, source index register, destination index register, stack based point register. The different status a process can be in as you can see, we have 1, 2, 3, 4, 5, 6, and the information XV6 tracks about each process includes its register context and status pro. We have, as you can see, start of a process memory, size of process memory, bottom of kernel stack, and process state, process ID, process information, if non-zero. So as you can see, we have a lot. I think I can show you in the Linux also. Let's go back in the Linux. Let's close this now. In the Linux, let me close this. Download here. So I think here. Let me open the terminal. Okay, open in terminal. So what we have seen now, I will show you here. Let's see. As you can see, all are here. So if you want to see, let's see proc H, yeah? Proc.h. Sorry, RV, sorry. Proc H. So you see structure of CPU. What we have here? The structure of structure context. For us, this structure proc, this one is the second one. This one the same. This structure proc, as you can see, it's all included, right? It's all included, as you can see. Size of process memory, structure, bottom of kernel, stack, and current directory. All is here, but that one I want to see. This one, structure context. We have only 5. You see, 1, 2, 3, 4, 5. But here we have a lot, yeah. This one we have a lot in the node. We have a lot. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, but here we have only 1, 2, 3, 4, 5. So EDI, destination index register, and something like that, but the different state of the process, we have 5. I think yeah, we have also 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, zone B, running, runnable, and so on. So this is what I have to show you. Okay, so this is what I wanted to show you. So in this way you can see, even you are allowed, you can download the XP6 okay, the XP6 operating system, and you can run it in your system. But this is what I want to show you. So in summary, what we have introduced the most basic abstraction of operating system, the process. It is quite simply viewed as a running program. With this conceptual view in mind, we will now move on the nitty-gritty, the low-level mechanisms needed to implement process, and the higher-level policies required to schedule them in an intelligent way. By combining mechanism and policy, we will build up our understanding of our operating system, virtualize the CPU. So this book is just for educational purpose from Hello Academy and Brain Boosters, and it is from OSTP book written by Remzi and Andrea at the University of Wisconsin. So next time we will continue to chapter 5, and till then I really appreciate and thank you. This is Engineer Selassie from Hello Academy and Brain Boosters. Thank you.